Hello, everyone. Welcome. Thank you so much for joining us today. We're just giving folks a few minutes to join the webinar, so please hang tight. We'll be getting started shortly. Hello, everyone. Welcome to today's AI4 webinar brought to you by SigOpt, an Intel company. We are so excited to have you all here with us. I have a few quick housekeeping items before we jump in. So while you're listening to the webinar, please make sure to ask your questions in the Q&A box as opposed to the chat. This is the best way for us to organize your questions so that we can get to as many as possible. Thank you so much. All right, it's time to get started with our topic of the day, which is intelligent AI experimentation. Learn how to design, explore, and optimize your models. Today's webinar will be presented by Scott Clark from SigOpt, an Intel company. I'd like to go ahead and welcome Scott to our virtual stage.
Hello, and thank you. Excellent. I'll start sharing my screen here and then we can dive right in. Perfect. Well, welcome everybody. Thank you so much for joining me this morning or afternoon or night, depending on where in the world you are. As was mentioned previously, my name is Scott Clark. I'm founder and GM of SigOpt, a company that was acquired by Intel last year. I'm going to tell you about intelligent experimentation, what it is, why it matters, how you can start using it today, and really how it can be utilized to supercharge all of the modeling efforts throughout your businesses. But first, before I dive too deep into that, I'll tell you a little bit about how I came to be standing in front of you today. I've been working on this problem for more than a decade now, all the way back to my PhD at Cornell, where basically I ran into the same problem over and over again. I was in the applied math department, and what that meant was getting a bunch of smart people from around the world to collaborate on a bunch of different things. We build great models in bioinformatics or finance or just kind of some of the early days of machine learning. But often after the cool domain-specific and expert-intensive work was done, it was left to the grad students, like myself, to go in and fine-tune and tweak all of these different models, do the grunt work of dialing it in to get slightly better papers, slightly better conference results, etc. We jokingly called this process grad student descent, and it often was just trial and error brute force, tuning hyperparameters, tuning architecture parameters, basically just doing tweaking of knobs to try to get, again, slightly better results. And I saw this as super prevalent across the entire department, and it was a huge waste of both grad student time, which I guess is free, but also computational time. Massive swaths of computational resources were used in this brute force approach. I was a bit surprised after graduating to literally see the exact same problem at Yelp when I joined their ad targeting team. There they had big search systems, advertising systems, spam detection systems, but again, big complex models that have been developed sometimes over many, many years, but lots of different tunable knobs and levers in them. The main difference between what I was doing in grad school and what I saw at Yelp, though, was if you could get these knobs and levers just right in industry, instead of getting a slightly better paper, you could get a lot of money out the other side. And this led me to package up some of my graduate thesis and open source Mo, or the metric optimization engine. This was one of the first open source Bayesian optimization algorithms and became pretty popular pretty quickly. And I went around the Bay Area and basically found this wasn't a problem isolated to my graduate research or even Yelp, but it was really a very prevalent problem around the industry. People were building all sorts of different machine learning algorithms, reinforcement learning algorithms, algorithmic trading strategies, and they all had these tunable parameters that affected the performance that were completely orthogonal from the domain expertise required to build those models. So you could know everything in the world about computer vision or natural language processing, but setting the right learning rates, setting the right decay parameters, et cetera, was this inherently trial and error-based process. That led me to start SigOpt about 7 years ago. We went through Y Combinator. We're venture funded by Andreessen Horowitz a few times and other venture capital firms, and ultimately led me to Intel today, where we're taking a lot of that same core technology and really trying to open it up and bring it to more and more people. So SigOpt is available for free today, and I'll talk about the problem we solve and how you use it towards the end in a quick demo. But it's really about solving this problem of experimentation and how to do that more efficiently. So to put this in context, I'll show Intel's version of the machine learning journey slide. I'm sure you have seen many versions of this over the years. Basically, the takeaway here is it's a very complex, very multi-scale problem. There's many different things that go into producing a machine learning model. But at the end of the day, what I'm going to be focusing on today is experimentation. Again, this part of the stack where it's about trying different topologies, trying different models, trying different data augmentation techniques, and ultimately tuning hyperparameters or the various inputs to a system in order to get to the best possible results. This is an inherently iterative process itself, where you're trying to basically decide what's the best thing to do next. Modeling is a scientific process, very different than traditional software engineering. It requires a lot of different experimentation, whether it's hypothesis testing, different data sets, different models. We're doing more applied optimization to tune hyperparameters or neural architectures to get to a specific result. But this experimentation requires tooling, it requires ways to do it more effectively. It's no surprise that when data scientists are often surveyed on where they spend a majority of their time, a lot of it goes into things like model building or deployment, et cetera. But a huge swath of it also goes into tuning, experimentation, or synonyms for this task of once you have something great, how do you make it as great as possible? And this is a really prevalent problem throughout industry. According to many different sources, while a lot of people are doing modeling, a lot of these models either fail to make it into production. Some of that can be because it never got to that peak performance that was hypothesized originally. This can be a casualty of bad experimentation. A lot of this is an incredibly manual process. Many businesses are employing very expensive, very rare talent in order to build models, and a lot of time is wasted doing this more brute force or trial and error based approach, or trying to reinvent the wheel and build their own optimization and experimentation systems. And ultimately, this is a problem that's tough to scale. Even if, like myself as a grad student, you can solve this for one specific problem, that's very often not the only problem that a business cares about. Many businesses are deploying dozens of different models. Every single one of them is different. Even if you can get the intuition and domain expertise to tune one of them, that doesn't necessarily translate to the next or the next data set or the changing market underneath you, especially in adversarial fields like algorithmic trading, finance, spam, et cetera. So ultimately, what this is about is making the modelers more efficient, more productive, get better insights, faster time to model, et cetera. Taking this flywheel of experimentation, helping it spin a little bit faster, and ultimately delivering higher ROI. This is part of, again, as I mentioned, a larger part of a big ecosystem of different modeling tools. These are all the different tools that Intel offers today. You can see that SigOpt sits near the top of the stack here, helping people with this experimentation task. It's worth noting, and I'll point this out a couple of times, but this can easily bolt on top of any kind of modular part of any modeling stack. And so oftentimes better experimentation ends up having a multiplicative benefit on top of other optimizations that you're doing. An example here is taking a data set using traditional XGBoost and using the Intel optimized variant, got a 20x speed up in training time. But by then also applying SigOpt on top of it, we were able to get another 1.5x, and that's multiplicative. So it ended up being a 30x speed up over baseline by combining these different things. So any pairwise or combinatorial combination of different technologies can have this nice multiplicative effect, and having it an intelligent modular way to do experimentation can really supercharge your model no matter what you're doing underneath the hood. As I mentioned before, this has we've been working on this for the better half of a decade now, and we have happy customers and users in research and industry and academia, really helping do the three main tenets of intelligent experimentation: designing, exploring, and optimizing. And I'm going to focus a lot on this today. But first, let me take a quick digression here and just, again, really iterate how easy this is to bolt on top of a system that you have in place already. So there's a training environment over here on the left. This is your data. This is your model. This could be in a cloud. This could be on-prem. This could be some hybrid solution. But there's something that you're doing today already, some modeling. Data comes in, some set of results come out. So intelligent experimentation, and SigOpt in particular, is all about just bolting on top of this and helping you make better decisions with your data, with your modeling, with this experimentation. And so metadata like metrics, parameters, data sets, things you want to track and keep in a system of record are sent to SigOpt, but the underlying data set and training isn't. That stays on your environment. Based off of the information that we receive, we, with our own proprietary optimizer or any open source optimizer you want to bring to the table, suggest the next set of things to try, and this process is repeated. This optimization feedback loop allows you to be guided into the best possible solutions while keeping analytics and a system of record of everything that you've tried so far to help you design better targets, get more intuition out of your models, and ultimately lead you to better feedback loops, better optimization loops, and better models. And again, widely used internationally for production use cases. We help US government agencies, over $1 trillion worth of hedge funds, Fortune 500 companies, hundreds of universities around the world. This has been a tried and trusted technology. And really one of the differences, I'd say, between some of my PhD work and some of the great academic open source that still exists today is we've really attacked this from a very industry and applied angle. From building SigOpt 7 years ago, instead of just solving the academic problems that allowed us to publish our dozens of papers from SigOpt, we've also really applied real industry problems to this as well too. So this has led us to develop many different technologies that don't just attack this from an academic standpoint, but really help all of these different firms solve their modeling problems in a real applied way. So that's some background on SigOpt and why intelligent experimentation is important. And now I'm going to dive quite a bit deeper into what it actually means, what it means for the modeler, all the different tasks that go into intelligent experimentation, and then go into the demo to show how in only a few minutes with a free account, you can be up and running and using intelligent experimentation yourself. So first up, experimentation. There's many different things that go into this. It's around both just having a system of record, like I mentioned before, tracking your work, It's about gaining insights from things that you've tried before. It's about tuning various aspects of your system. It's all of the different kind of scientific process that goes into this. Intelligent experimentation, though, is about taking that whole process of trying different things, of really modeling, and doing it in a way that helps augment the expert. So helping make recommendations for what to try next, helping make design decisions for different metrics to optimize next, helping explore and analyze the underlying response surfaces and how these different input parameters actually affect what you actually care about at the end of the day. So ultimately, it's about helping you take kind of the art of like doing this like alchemy and pulling it into a science like chemistry. It's about not just having a system of record or a way to track your experiments, but really it's about having a collaborator to help you get the most out of your experiments. And as I mentioned before, there's really three main pillars to this. It's design, explore, and optimize. So design is about asking the right questions. This is the number one most important thing about experimentation and optimization more generally. The best thing about an optimization method is it'll help you hit a result. And the worst thing about it is it will blindly help you hit that result, whether or not it was what you actually wanted to do or not. So if you just blindly tune towards accuracy, you could potentially make a model that was way too complex or take way too long to train or infer. If you just blindly tune towards making as much money as possible, you might sacrifice a user experience. So really designing experiments is the first and most fundamental part of experimentation. The second pillar is about exploring. So as you're designing, as you're trying different things, as you're looking at the outputs, exploring is about seeing how all of these things these different things interact, making sure that you don't have this gotcha of accidentally shooting for the wrong target or not understanding how all of these different things come together. So exploration is about understanding. And finally, optimization is once you have designed an experiment, once you understand that experiment, how do you just get to the best result as quickly as possible? This sometimes leads to new insights, which allows you to design new experiments, et cetera. And so this experimentation flywheel continues. These are things that are often being done today, as I mentioned, whether via kind of intuition, via brute force like grid search or random search, or via cobbling together and reinventing the wheel with different open source algorithms, et cetera. SigOpt and intelligent experimentation is about just taking those processes, making them more efficient, and really shining a light on them. So I'll dive into each one of these things individually to give some examples, and then go on to the demo. So first up, in designing, again, this is about just setting up the problem, kind of understanding all of the different inputs that go into your system. So when you're doing modeling, when I showed that screenshot before, a huge part of the front end of the task is things like choosing the data. So what's the actual data set? How do we augment it? How do we clean it? How do we do different feature engineering? A lot of these things themselves have different tunable parameters associated with them, especially once you start to look into transformers or different applications like text or vision or audio. A lot of different things go into this. So even just designing what it is that we're going to try first can sometimes be a very difficult problem. Choosing the right model, again, becomes a very difficult task, whether using kind of traditional machine learning or statistical-based approaches, more deep learning-based approaches, maybe reinforcement learning, maybe some custom proprietary ensemble. Again, many different things go into the model itself. And of course, every single one of these models has its own tunable parameters, whether it's architectural parameters or hyperparameters. And finally, kind of deciding how you're actually going to have this model train. What's the loss function? Like, what is it that this model is going to be trying to do, taking in all this data in order to come up with some sort of generalizable end state that you can use in production. So again, many different kind of standard and more esoteric ways to even have this model do its training itself before we're even trying to come up with production metrics. So how do you get all this right? Well, the answer is you don't. You try a bunch of different things, and what's important is tracking the results, tracking the trade-offs that you made, and understanding that in order to make progress. So ultimately, you're not going to get this right the first time, but the important thing is to remember, if you got it right on the 7th iteration, what exactly you did, how to go back to that, how to repeat it, how to reproduce it, how to share that with a colleague that has a similar problem, etc. So with a few lines of code, all of this information can be tracked within an intelligent experimentation platform like SigOpt. So again, taking the data that might already and model that already exists today, now we're just, again, keeping a system of record of all the different design choices that were made. And we can start to see individual trade-offs, which really starts to bring us into the second pillar of intelligent experimentation, which is exploration. So again, this is more than just fitting the model to the data. This is more than just running through this once. This is about kind of understanding all of the different outputs that can come from the inputs we decided in the design stage. So these outputs or metrics have their own life cycle. Different metrics might be too simple or too high cost. They might not actually be generalizable or faithful to an outside data set. They might not be proximate or precise. They might decay over time. They might have diminishing returns on 99.9999%, et cetera. And ultimately, our goal is to be able to figure out in the exploration phase what metrics actually matter and what is it that we're actually trying to shoot for. Again, the best thing about an optimization algorithm is being able to hit any target. And the worst thing is you have to design the target. Otherwise, it will just hit whatever target you give it. And that might not be what you actually care about in production. So as I mentioned before, there's many different metrics, even in the training stage, that you might need to think about, whether you're doing kind of classification or regression or some other task, making sure that you're actually, that this model itself is converging to something that ultimately generalizes to what you care about. Beyond that, there's different ways that these metrics can converge to that ultimate model. So the stability of how well that model is able to come to that result has an impact. You don't want a model that just got lucky on one kind of random permutation of a gradient boosted machine or a stochastic gradient descent algorithm, et cetera, but has this very unstable point that ends up not generalizing to the real world. So what you're shooting for and how you got there matters and is worth tracking. Ultimately, validation metrics are the common thing that people end up optimizing. So this could be a holdout data set, this could be a simulation, this could be things like AUC or an F1 score, or kind of the reward function of a reinforcement learning task. But ultimately, these are the expensive metrics to calculate. After you've done the training, you pipe it into some other data set, and you see how well it performs on some metric. And there's many different ones, as I mentioned before. Oftentimes in a real business application, you're not just trying to overfit ResNet to get a slightly better accuracy to publish a paper. What you're trying to do is trade off accuracy and performance and simplicity and user experience and all of these different things that you can calculate after the model is actually built. So beyond these metrics that you might actually want to optimize, there's often guardrail metrics or constraints. So not only do you want the best model, but you want the best model that fits within whatever business context you have. So we see this often in material science, in edge models, in models that need to perform in a very quick fashion, like in the algorithmic trading space, et cetera. There's often things that you want to optimize, and there's things that you just need to be true. The model can't be larger than a specific size. The model has to have a specific inference. The model has to have a very specific interpretability, et cetera. Within those constraints, you want to maximize these other metrics, and you don't really care about these metrics beyond that they're satisfied. So you're not really trying to minimize or maximize them, but these can provide guardrails in order to get you to whatever business result you're actually looking for. And this is one of the nice things about SigOpt is it allows you to put in dozens of different metrics, optimize many of them, put guardrails on many of them, track many of them, and be able to do all of this simultaneously. Finally, of course, as well, after you've set up these guardrails, after you've kind of zoomed in on the part of the space that you actually care about, are production metrics. So these are the metrics to see how the model's actually done in the real world. Oftentimes, when you're designing a model and putting it into production, you're not actually trying to climb some static mountain and finding some peak best model that's ever existed, and then you're done with your job forever. What you're really trying to do is surf a wave. The data is changing underneath you, the environment is changing underneath you, you have competitors in the market, et cetera. What was best a year ago might not be best today. So production metrics can help you keep track of, this is how well I did in training, this is how well I did in testing, but this is how well I did in production as well. And that can help you draw these correlations, really explore and get that insight into how we can ultimately phrase our optimization experiments moving forward, and how often we should rerun them as well too. Which leads me to, there's lots of different ways to view these metrics, as I mentioned before, but this leads me to optimize, the third and final pillar of intelligent experimentation. And this is about, again, once we've understood our input space and understood our output space, kind of understood what it is that we're trying to achieve, and we can phrase that as, I have these inputs and I want these outputs, maybe maximize, minimize, these guardrails, whatever these things I just want to track, et cetera. But we can phrase it as a optimization problem. Now it's, how do I get there as quickly as possible? Oftentimes, these problems end up having dozens of different parameters. There might be dozens of different metrics to tune, things that quickly become intractable. Brute force grows exponentially with the size of the input space. Humans end up being pretty bad at doing 10-dimensional optimization in their head. And at the end of the day, every single time you want to try something, that could be hours or days of computational time cost as well. So efficiency is the name of the game here. And at SigOpt, we've developed and published and patented and continue to push the state of the art of different Bayesian and global optimization techniques. So underneath the hood of SigOpt is an ensemble of different techniques that automatically trade off exploration, so learning about your model, and exploitation, driving you to those results that you've set up, and get you as efficiently as possible towards the configurations that actually solve the problem as you stated. What we see in practice is this is usually a couple of orders of magnitude more efficient than more traditional brute force approaches, and about an order of magnitude more efficient than a single Bayesian or global optimization technique. The intuition there is, by being able to apply different techniques and auto-tuning the optimizer to your problem, you could do quite a bit better than just applying a one-size-fits-all single approach through the optimization literature. Again, easily bolt on top of anything underneath, can tune towards any metrics, any application, whatever it may be. All of the modeling and data stays on the customer side. We hinted at this before, but one of the key things that we've done a lot of work in, and a lot of our papers actually end up being about it, NeurIPS and ICML and all of these machine learning conferences, is around real applied optimization, like I talked about before. So what we found over the better half of the last decade is people have many different metrics, and optimizing all of those different metrics really matters. Larry spoke at length about this, so I won't go into more detail. Another thing worth pointing out, though, is intelligent experimentation is really bolstered by optimization, and that's why we've put a lot of time and research with our full-time research staff into our optimizer. But there's many different optimizers out there, and some of them work very well for certain problems. So bringing your own optimizer or doing some sort of hybrid trade-off of different optimizers is also something that the intelligent experimentation platform that we've built supports. So if you already have your favorite optimizer out there, it's very easy to bolt that into the system as well too, with a few lines of code. Or trade-off, or try both. Intuition here is 2 is often better than 1, especially if you have the computational resources to try both. Given the scope of this talk and the audience, I'm not going to dive into a ton of these different aspects of our optimization algorithm. As I hinted at before, there's 100+ research years have been put into this from our research team over the many years that SigOpt has existed. Many different great papers, great talks, and things like that. If you want to learn more, sigopt.com/research has quite a bit of our work and the work of our collaborators. But again, the takeaway here is real world optimization problems often look different than toy academic optimization problems, and you need different tools to attack them. And that's really what we've developed, is robust industry tested tools to attack those hard optimization problems within SigOpt. So fundamentally, again, the 3 pillars are about designing, kind of understanding and asking the right questions, exploring, understanding the outputs and getting intuition, and just kind of understanding about your models themselves, and then using that to do efficient optimization, repeating this process. So intelligent experimentation can, again, just accelerate what's already being done today, help you get past whatever plateau you might have found in your own experimentation, or just free up your time and energy to do more of what really differentiates you and your models. As I hinted at earlier, this has been used in a wide variety of different industries. Different firms tend to get different values out of intelligent experimentation. While all 3 of these pillars resonate with anyone doing experimentation, sometimes it's just about designing the right experiments. So Numenta is one of our big customers, and they were able to take a well-understood model like ResNet, and by doing a different design of experimentation than historically done, specifically around the sparsity of the neural network itself, they were able to both optimize for accuracy and get an extremely sparse model. So again, opening up that design space really enabled a very significant business output. Another one of our big users is PayPal. Here it was really about exploration. So there was the working in graph neural networks, a relatively new field, one that's continuing to be understood. Here it was about tracking a wide variety of different metrics. So there were up to 50 different metrics were being tracked to try to kind of understand all of the different things that might actually matter for the in business use case here. By doing that, by visualizing that, by kind of understanding the correlations and input-output space, they were able to design an experiment that ultimately led to significant business results. But here it was about taking something that ahead of time they didn't necessarily know what they were shooting for, and using intelligent experimentation to gain that understanding through exploration. Finally, optimization. A lot of our bread and butter is about kind of getting to the best results as efficiently as possible. So Two Sigma, one of our big longtime customers in the algorithmic trading field, uses SigOpt all the time to get better results for the algorithmic trading and machine learning models. They find that it's about an order of magnitude faster than different open source techniques that they've adapted over the years, and is able to run on their extensive infrastructure, doing asynchronous optimization across 100+ individual computational resources simultaneously. And this is again about taking something that was already good, and developed by, in this Two Sigma's case, hundreds of intelligent PhDs that know their field better than anybody else in the world, and providing this boost and having them break through the plateau of experimentation that they might have been stuck at before. So we've talked about SigOpt, we've talked about intelligent experimentation, all of the different things that go into this, whether you're a modeler or you're a manager of modeling teams today. I can guarantee that these are problems that are either being actively worked on or things that are being actively ignored. But fundamentally, there's solutions out there. In this next few slide demo, I'm going to show you with real code how with just a few lines of code, you can get all of the benefits that I just talked about. So again, SigOpt is completely free, so you can feel free to follow along as you go, sigopt.com/sign up. And you can be getting the benefits of intelligent experimentation probably before we're done with the Q&A session. So for the purposes of the demo, I'm going to show a super simple data set using a super simple model. Again, this can be applied to any data set, any application, any model. But for the purpose of the demo, I'm just going to take XGBoost, tried and true gradient boosted machine method. I'm going to take the breast cancer data set from scikit-learn, so kind of one of the classic teaching data sets. And we're going to try to do some experimentation to create a better classifier. So first, here's the entire model, data set loading, model, et cetera, in a few lines of code. We're loading the data. We're showing how you can instantiate SigOpt to start tracking things like what data set was used, which model was used, et cetera. Then we're actually going to create the model and train it and start looking at the outputs. Again, with one line of code here, we're starting to log specific things that might be interesting for the model itself. What I'll zoom in here for a second, though, is this model has tunable hyperparameters. I've shown 3 here, but there's really dozens in XGBoost and in any machine learning model that you might have. They might have intelligent defaults. They might have defaults that just run very quickly for tutorial purposes, or they might have defaults that were set for a very specific model. But at the end of the day, this is what you can tune and tweak to get boosted performance. So traditionally, a lot of times when we talk to firms, the data scientists are trying to do this themselves, manually, brute force, something like that. With a slight modification here, now we're tracking all of the different inputs that are going into this model. We're able to see what all the different hyperparameters went in to affect the outputs that we're tracking below. This allows us to do things like manual search, as people often do today, or grid search or random search or something like that to kind of gain that intuition. And this really allows us to do these first 2 pillars of intelligent experimentation. We've designed our experiment. We have different outputs that we're looking at. We might have tried a handful of different configurations via intuition or via a grid search or parameter sweep type method. We can start to kind of understand how the inputs affect the outputs. We can start to look at all of the different metrics and start to design an experiment that we might actually care about. We might want to say, hey, I want the best recall across both classes because it's a medical use case and recall might matter a lot. But I also want the accuracy to be as high as possible. So by tracking everything, we can start to be able to phrase these questions more intelligently as opposed to having it all be intuition based. And that's what we do here in this final code snippet. We take the exact same data set and model that we had before, but we create a SigOpt experiment around it. So instead of manually trying different hyperparameters for the number of estimators, the depth, and the learning rate, now we're going to tune them across some bounds that are set, and we're going to maximize for accuracy. We're going to maximize for these recall parameters. We're going to put thresholds on some of these parameters. We're just going to track a handful of them, we're really going to use the full suite of different optimization techniques. And in about 30 different attempts of this experiment, running through and trying different things, either sequentially here or asynchronously in parallel, we're able to quickly get to these results. So in the upper right here, we have different configurations that are Pareto optimal with respect to the different recall parameters, and the colored dots here are the ones that satisfy that accuracy threshold that we had set. So we went from tuning and tweaking in the dark, maybe not even keeping track of what we were doing, trying to do it all in our head, to having a system of record for reproducibility, for exploration and understanding. And then ultimately, we're able to phrase this as an optimization problem and very quickly get to two results that could then be further explored or put into production for this model. Again, taking a simple model that you could see in an XGBoost tutorial, and with less than a few dozen lines of code, have taken it all the way to this state-of-the-art result. So again, quickly designing, with a few lines of code, exploring via our dashboard, and optimizing via our algorithms or any optimizer you want to bring yourself, you can get to these results. So as I mentioned a few times throughout the talk, SigOpt is completely free. This is one of the great parts about being part of Intel. Instead of being a standalone startup with a goal of trying to make as much money as possible, now we're part of Intel, where our goal is to help enable as many modelers as possible. So what was before an enterprise-only solution is now completely free worldwide. Anybody can sign up today and use SigOpt free forever. And again, few lines of code and you'll be up and running. Another thing before we go into the Q&A that I want to call out is we're doing our first AI and HPC Summit. We have a bunch of different firms from industry and academia coming to talk about how they apply intelligent experimentation to their problems and how they've been able to publish better papers or get better results in their businesses by using intelligent experimentation. And we're really excited for this. Completely free, completely virtual. All the talks will be recorded. It'll be on November 16th, and hope to see a few of you there. So that's it for me. Thank you so much for your time today. I look forward to hearing any questions that went into the Q&A system. I'll leave this slide up here for anyone who's interested to sign up for this as well too.
Amazing. Thank you, Scott. A big virtual round of applause to you. That was awesome. We do have some questions in the Q&A box, so I will go through a couple of them. So the first question is, could you explain where SigOpt fits in the AI tool ecosystems? For example, Neptune AI, weights and biases.
Yeah, great questions. So this is a big problem, very prevalent problem. It's become a very popular problem over the last 7 or 8 years. I'd say the main difference between SigOpt and other experimentation tools is this concept of intelligent experimentation. So again, it's not just about having a system of record or a place to track what you've done, but it's really about having a collaborator helping you get to the best possible results. While we also have a system of record and also allow you to do a lot of this tracking, some of the benefit that we provide is by also doing the optimization, by using what we've tracked to inform the optimizer, by really having this this flywheel type effect where we're able to do more than just track, or just have this kind of thin pipe between an optimizer and a tracker. By putting it all together, you get more than the sum of its parts. And big fans of everything out there, big fans of experimentation in general, but intelligent experimentation is our focus as opposed to just tools for experimentation more generally.
Excellent, makes sense. All right, the next question is, are your clients really interested in experiments as you've defined it? Or are they simply interested in tuning their models just enough to be able to hit their targets, either for the model itself or the KPI it informs or influences?
Great question. So at the end of the day, oftentimes it's just about getting results. The method to get to those results is experimentation. So they care about experimentation insofar as it helps them get value that was otherwise left on the table. We have so many different stories, and you can hear more at the summit of people who might have hand-tuned models over years sometimes, and we're able to get better results by using intelligent experimentation. So literally just taking value that was being left on the table. But again, experimentation is a means to an end. At the end of the day, what you really care about is getting that better result, getting that better KPI, whatever it may be. And so what SigOpt allows you to do is do that as efficiently as possible, not make you reinvent the wheel, and help you get to that end as quickly as possible. And yeah, that's really the crux of what we're doing, is helping you do your job better and focus on what you're great at.
Awesome, thanks. All right, our next question is, how does the optimization actually work?
Yeah, great question. So I hinted at this a little bit in the Bayesian optimization section, but it's really about taking all of the inputs from what we've observed thus far. So this is through the design and exploration of experiment, or we can even try to warm start this or cold start this for you. But it's really about understanding how these inputs affect the outputs that you have. So it's about exploring and learning as much as we can about that relation between the inputs and outputs, and then exploiting the information that we've gathered in order to drive you to better and better results. So there's many different methods out there, from Gaussian processes to tree-Parson estimators to genetic algorithms. I highly recommend checking out sigopt.com/research or all the great workshops at NeurIPS and ICML and things like that to dive super deep. But fundamentally, it's about how do we take what we've seen so far to try the most intelligent thing next, and then use that to update what we've seen and repeat that process to intelligently search the space.
Wow, that's awesome. And then we have another question. Can you give more examples of how intelligent experimentation has worked in the real world?
Perfect lead into the SigOpt AI and Hpc Summit. So again, here we have a handful of different firms that have used SigOpt either for real world industry applications, for academic applications, research applications, etc. This is a small microcosm of all of the users that we've had use SigOpt over the years. So I highly, again, recommend checking out sigopt.com. On the research page, there's dozens of papers that have used us. On our main pages, we talk about some of the industries that have used us. But I can almost guarantee that whatever problem you have today is something that we've heard about or seen before, and something that we can help with.
That's amazing. That's really exciting stuff. All right, we have another question. In cases where you inherit a working model, how can SigOpt assist in any improvements when you may not have access to the original or historical design and model info?
Great question. So it's better to start late than never, I guess is the answer here. So you have at least one data point, and that's whatever magic numbers are currently checked into Git for that model today. So that is your first data point, the first thing that you can start to track. From there, you might be able to start tracking passively other metrics that this model kicks off. So now all of a sudden you have only one input configuration, but now you have a handful of different things that you might be able to start tracking. Then you can start to tune and tweak things, do different A/B tests if this is a model that's being run live, or just start doing simple exploration-based optimization approaches at the very beginning. But I'd say this will help whoever you invariably eventually give this model to down the road to be able to say, this is what I've tried, here's how you reproduce it, here's the trade-offs that I made, etc. But I would say just start now, and you'll thank yourself, and whoever the person who inherits this model from you will thank you later.
I love that. Definitely better late than never. That's awesome. And then another question is SigOpt an MLOps tool?
Yeah, so MLOps means many different things to many different people in the same way that AI means many different things to many different people. So oftentimes people do include optimization or hyperparameter tuning as part of an MLOps tool chain. What we are not, though, is we're not an end-to-end MLOps solution. There's many great tools out there. Intel has many great tools like Converge that do this for firms. We're very focused on the experimentation problem. So we're an MLOps tool insofar as experimentation is a component of MLOps, but that is our focus, and we want to be the best in the world at that, and be the first to develop this fully intelligent experimentation solution. So as this field continues to grow, though, we're very excited because we can modularly bolt into a lot of different MLOps platforms, whether it's Converge. You can use SigOpt as part of like Raytune, whatever it may be. Experimentation, if it's a component, we can bolt into it.
Amazing. And there's a follow-up question that's kind of along that same line. Would SigOpt also work with H2O AI or other AutoML platforms?
Yeah, so yeah, we've done integrations with H2O in the past. And so the short answer is yes. If you can write code, if you can access the internet, if you can wrap a for loop around whatever model you have, then you can use SigOpt, and it can readily replace in-house more brute force or more naive optimization methods. In the pure like GUI drag and drop version of AutoML, obviously that would need to be a tighter partnership, which we're talking to a handful of firms about. But if you can write code, then you can use SigOpt.
Very cool. All right, another question. Is SigOpt planning on contributing metadata through its platform in support of forming standards of trustworthy AI?
Good question, difficult question, open-ended question. Yeah, so I mean, we're active contributors to the academic community. Our research teams at Informs right now, talking to a handful of papers that they're presenting. We go to half dozen or more conferences a year to present our work. We're also big contributors to the open source community. And this is something that's ethical AI, explainable AI are things that are very important to us. So we'll continue to push work out here. And it's something that's very important to the team in general, kind of giving back to academia, giving back to the community, the giants whose shoulders we rest on. And so while we don't have anything specific for that exact outcome right now, it's something that we're continuing to actively explore, and I know is important for Intel as well.
Awesome. And for the audience, a couple people have asked if the recording will be made available. That answer is yes, it will be made available, and you should be receiving it via email within about 48 hours of the end of this session. Any other questions that anyone would like to submit? Let's see. Okay. 1 second, just sorting through to see what other questions we have coming in. Okay, so some people are wondering if the deck will be made available. I think that's up to you. Awesome. All right. So yes, the deck will be made available and shared. So please hang tight. We'll get you that information. Thank you. All right. All right, anyone else have any other questions to submit? You can use the Q&A box. We are monitoring this live so that we can answer your questions, but this has been a great conversation. I know this audience has learned a lot. I've learned a lot, and it's amazing to see what you all are doing in this market. It's very important work, so I know it's a very exciting thing to be a part of.
Thank you so much, and thanks everybody who asked questions. And again, feel free to try it out yourself. Sometimes doing is the best way to see how things actually work. So we're available to answer questions as they come up, either here or at our summit as well.
Awesome. All right. Well, thank you again for sharing this with us. Scott, this has been awesome. And we really appreciate you taking time to share all of this and to share these amazing resources with us. Again, a huge virtual round of applause to you. And we really appreciate your time today.
Thank you so much. It's a pleasure as always.
Thank you. And for the audience, we thank you so much for joining us today. Please stay tuned for future AI4 events and keep an eye out for the SigOpt amazing summit that's coming up. We hope that you'll be able to join that as well. So thank you again, and we look forward to seeing you soon. Have a great day.